The internet, it's become an indispensable part of our lives, connecting us in ways we never imagined possible. We use it for everything from communication to commerce, entertainment to education, whether it's shopping online, attending virtual classes, or staying in touch with loved ones through video calls. The internet is at the heart of it all. But have you ever stopped to wonder how it all works? How does data travel from one corner of the world to another in the blink of an eye? Behind the scenes, a set of rules governs how data travels across this vast network. These rules ensure that information is sent and received accurately and efficiently. This set of rules is known as the TCP/IP protocol stack. It's a fundamental framework that makes the internet function smoothly. TCP/IP stands for Transmission Control Protocol Internet Protocol. These protocols are the backbone of internet communication. It's a suite of networking protocols that forms the foundation of the internet. Without TCP/IP, the seamless exchange of data we rely on daily would be impossible. Just like a postal system has rules for addressing and delivering mail, TCP/IP provides a standardized way for computers to communicate with each other across networks. It ensures that data packets are correctly addressed and delivered to their intended destinations. The TCP/IP protocol stack operates in layers, with each layer performing a specific function. This layered approach simplifies the complex process of data communication. This layered architecture allows for modularity and flexibility, making it possible for different types of networks to seamlessly connect and exchange data. It enables diverse devices and technologies to work together harmoniously. Whether you're browsing the web, sending an email, or streaming a video, TCP/IP is working behind the scenes to ensure that your data reaches its destination. It handles the complexities so you can enjoy a smooth online experience. Understanding the basics of TCP/IP is essential for anyone who wants to gain a deeper understanding of how the internet works. It's the first step towards mastering the intricacies of network communication. In the following sections, we'll delve into the key components of this protocol stack and explore their roles in enabling global communications. We'll break down each layer and explain how they work together to make the internet the powerful tool it is today. At the heart of the TCP/IP protocol stack lies the Internet Protocol, or IP. This fundamental protocol is the backbone of the internet, enabling seamless communication between devices across the globe. IP is responsible for addressing and routing data packets across the internet. It ensures that data sent from one device reaches the correct destination, no matter how far apart they are. Think of IP addresses as the street addresses of the internet. Just like every house has a unique address, every device connected to the internet has a unique IP address. Every device connected to the internet has a unique IP address that identifies it on the network. This unique identifier allows devices to find and communicate with each other. When you send data over the internet, it's broken down into small packets. These packets are like pieces of a puzzle that need to be reassembled at the destination. Each packet contains a header with the source and destination IP addresses, much like an envelope has the sender's and recipient's addresses. This information is crucial for directing the packets to the right place. IP takes care of delivering these packets to their intended destinations, regardless of their physical location. It ensures that data can travel across different networks and reach the correct endpoint. IP operates at the network layer of the TCP/IP model. This layer is responsible for the logical addressing and routing of data, making sure it gets from point A to point B. It's a connectionless protocol, meaning that it doesn't establish a dedicated connection between the sender and receiver before transmitting data. Each packet is sent independently, without prior arrangement. Instead, each packet is treated independently and routed through the network based on its destination IP address. This allows for flexible and efficient data transmission. This connectionless nature of IP makes it efficient for transmitting data across a vast and dynamic network like the internet. It can adapt to changing network conditions and find the best path for each packet. However, it also means that IP doesn't guarantee delivery or maintain the order of packets. Packets can arrive out of order or even get lost along the way. That's where TCP comes in. TCP, or Transmission Control Protocol, works alongside IP to ensure reliable data transmission, reassembling packets in the correct order and requesting retransmission of any lost packets. While IP handles the addressing and routing of data packets, Transmission Control Protocol, or TCP, provides reliable and ordered data transmission. TCP operates at the transport layer, one layer above IP in the TCP/IP model. It builds upon the basic packet delivery service provided by IP to offer a connection-oriented service. Before transmitting data, TCP establishes a connection between the sender and receiver. This connection acts like a virtual pipe through which data can flow reliably. TCP uses a process called a handshake to establish this connection and ensure that both parties are ready to communicate. Once the connection is established, TCP takes care of segmenting the data into packets, numbering them, and sending them over the network. It also handles error detection and retransmission. If a packet gets lost or arrives out of order, TCP requests the sender to retransmit the missing or corrupted packets. This meticulous approach to data transmission ensures that data arrives at its destination reliably and in the correct order. TCP is like a reliable courier service that guarantees the delivery of your package intact and in the order it was sent. Section 4. TCP Handshake and Data Transmission. Let's delve deeper into how TCP establishes a connection and ensures reliable data transmission. The TCP handshake is a three-way process that ensures both the sender and receiver are ready to communicate. First, the CN, or synchronization. The sender sends a SYN packet to the receiver indicating its intent to establish a connection. This packet includes a sequence number that the receiver will use to acknowledge receipt of data. Next, the SYNAC, or synchronization acknowledgement. The receiver responds with a SYNAC packet, acknowledging the sender's request and sending its own sequence number. Finally, the ACK, or acknowledgement. The sender sends an ACK packet back to the receiver, acknowledging the receiver's sequence number and confirming the connection establishment. Once the handshake is complete, data transmission can begin. TCP segments the data into packets and numbers them sequentially. The receiver acknowledges receipt of each packet, and if a packet is lost or arrives out of order, TCP initiates a retransmission. This ensures that all data arrives reliably and in the correct sequence. Section 5. User Datagram Protocol, or UDP. While TCP provides reliable and ordered data transmission, there are situations where speed and efficiency are more critical than guaranteed delivery. This is where User Datagram Protocol, or UDP, comes in. UDP is another transport layer protocol in the TCP/IP stack. But unlike TCP, it's a connectionless protocol. UDP doesn't establish a connection before transmitting data. It simply packages data into datagrams and sends them off without any guarantee of delivery or order. This makes UDP faster and more efficient than TCP, but it also means that data can be lost or arrive out of order. So, when would you use UDP? UDP is well suited for applications where speed is paramount and some data loss is acceptable. For example, UDP is often used for streaming media, online gaming, and DNS lookups. In these applications, a slight delay or the loss of a few packets is preferable to the overhead of establishing and maintaining a TCP connection. Section 6. TCP versus UDP. Choosing the right protocol. TCP and UDP are both essential transport layer protocols in the TCP/IP stack, each with its strengths and weaknesses. Understanding these differences is crucial for network engineers and developers alike. Choosing the right protocol depends on the specific requirements of the application. Factors such as reliability, speed, and the nature of the data being transmitted play a significant role in this decision. TCP is the go-to protocol when reliability and data integrity are paramount. It ensures that data packets are delivered in the correct order and without errors. It's like sending a registered letter with tracking. You can be sure that it will arrive at its destination safely and in the order it was sent. This makes TCP ideal for applications where data accuracy is critical. TCP is used for a wide range of applications, including web browsing, email, file transfer, and secure communication. These applications require the assurance that data will not be lost or corrupted during transmission. UDP, on the other hand, prioritizes speed and efficiency over guaranteed delivery. It is a connectionless protocol, meaning it does not establish a connection before sending data. It's like sending a postcard. It's faster and cheaper than a registered letter, but there's no guarantee that it will arrive or that it will arrive on time. This makes UDP suitable for applications where speed is more important than reliability. UDP is suitable for applications where some data loss is acceptable and speed is crucial, such as streaming media, online gaming, and voice over IP or VoIP. These applications can tolerate occasional data loss without significant impact on user experience. In essence, the choice between TCP and UDP boils down to a trade-off between reliability and performance. Each protocol has its own set of advantages and is suited to different types of applications. Understanding this trade-off is essential for designing and deploying networked applications that meet specific performance requirements. By carefully considering the needs of the application, one can choose the protocol that best balances reliability and efficiency.